This project is Modeling Asthma Risk in California, done in association with the Geospatial Lab at the University of San Francisco. According to the Center for Disease Control and Prevention, California has the greatest number of people affected by asthma in the U.S., totaling over 2.2 million. While the percent of the population affected is lower in many other states, the number of people is highest in California due in part to its large population. Asthma is a chronic disease that impairs breathing and can cause several health problems and even in some extreme cases be fatal. In this analysis, we attempt to model real-world asthma risk at the census block group level for the entire state of California. To do this, we've created a Respiratory Risk Index, or RRI, to identify locations that experience increased asthma rates and use GIS to map the results. Several studies have shown that age plays a significant role in respiratory illness. Also, there's consensus that shows proximity to roads can also affect respiratory health. The most widely observed gaps are due to the lack of high-quality, high-resolution health data, and this was a challenge for this analysis as well.
Our project examines possible correlations between California air quality, road proximity, and age demographics. Using public health data, we will determine if these factors can successfully model real-world conditions. And so, our research question is, how well do these three risk factors identify areas with high asthma risk, and do these areas correspond with actual public health data?
To answer this question, we first needed to gather several data sets from various sources. The age demographic data was obtained from the U.S. Census Bureau at the block group level. This had information about the number of households with certain age groups. This data was used to generate an age index that ranked the risk of asthma according to the percent population of sensitive groups. To identify areas likely impacted by roads, we obtained a data set from the California government on road utilization. We used this data to identify all roads that were used at a rate higher than the state average. Then we used the GIS Near tool to determine the distance between block group center points and the high utilization roads. After the distances were calculated, then we implemented a decay function to assign a road index value to all block groups within 1,500 meters. If a block group was closer to a high utilization road, it would receive an index closer to 1, and if it was closer to 1,500 meters, then it was assigned an index closer to 0. The final air safety index was generated from air quality data obtained from the California Air Resources Board, and it was the county level for most of the state. To calculate air safety index for each county, we aggregated the total number of days that were unsafe for all groups, then divided by the total number of days measurements were taken. This provided a county-level air safety index that was then assigned to all block groups within that county. These three sub-indexes were then combined to produce the final Respiratory Risk Index, or RRI. This is a value between 0 and 1 that should describe the overall risk of asthma according to the three risk factors measured. After each block group received an RRI, then we calculated the total number of houses within a block group that was potentially at risk. This was done by multiplying the RRI by the total number of houses within each block group.
This map displays the geographic distribution of respiratory risk index. This allows us to understand and compare RRI regionally. The maximum value for respiratory risk index value is 0.40. As for the minimum value is 0.17, and the average value for all counties is 0.32. This map highlights the potential impact on population given the respiratory risk index. The minimum value for a population at risk is 78 households. The maximum value is 1,186,000 households. The average for all counties is approximately 73,000 households. The kernel density map indicates regions with the highest level of respiratory risk. This allows us to identify hotspots. We can clearly see that high population cities have high respiratory risk. The hotspots in this map represent the Bay Area, Los Angeles, San Diego, Sacramento, and Fresno. The scatter plot displays the expected numbers of households at risk according to the RRI measured against observed hospitalization data at the county level. What we can see is a strong positive correlation between observed and expected values as indicated by the high R value of 0.94.
Our three metrics for identifying respiratory risk when combined into a single index seem to mimic real-world conditions when compared to hospitalizations caused by asthma. Our projected and observed numbers are closely related as shown by the high R value. This suggests that the model reliably predicts real-world asthma trends and that the three factors chosen for this analysis have a significant relation to asthma cases in California. A possible reason that hospitalizations are lower than the values predicted in the RRI could be that not every asthma case is severe enough to result in hospitalization. This suggests that the RRI value could be used in a predictive capacity to determine areas of potential risk, but perhaps not as a means of estimating the exact number of people affected.
For future studies, we can expand our research by adding accessibility to hospitals, point source polluters, and calculated weights for each of the sub-indices.